Hi, welcome you to module 4. In this module we will discuss some basic properties of a probability function. If you recall, in the last module we defined probability function using 3 axioms. Now we will use those 3 axioms to derive various properties of a probability function. So to begin with, I have 3 components of a probability space, which is the sample space omega, P of omega, which is the power set of omega, which we take as the event space, and P a given probability function. Now for any event E, we will define E complement to be the complementary of event E. That means it will have all those outcomes which are not favorable to E. Then I see the first property. The first property says for any event E, probability is always between 0 and 1. Greater than or equal to 0 is a part of axiom 1, but what we will prove is probability is always less than or equal to 1. Also probability of E complement is same as 1 minus probability of E. So to see that, note that omega can always be written as E union E complement. So for example, if I draw a Venn diagram, E is this set, then your omega turns out to be E and whatever is outside E. So omega is E union E complement. Not only that, you see this E and E complement are disjoint. So that means P of omega, which is same as P of E union E complement. Now using axiom 3, P of omega is 1. Since E and E complement are disjoint, using axiom 2, P of E union E complement is same as sum of the individual probabilities. Now I know that by axiom 1 probability is always non-negative. So P of E complement is always greater than or equal to 0. So this sum will always be greater than or equal to P of E, and P of E is always greater than or equal to 0 by axiom 1. So what if we combine all these 3 observations, what we observe is probability is always between 0 and 1. Now note that I have expression 1 is equal to P of E plus P of E complement. Here I can directly conclude that P of E complement is same as 1 minus P of E, provided I can take P of E on the left hand side, which amounts to cancelling P of E on 2 sides. That is possible provided P of E is finite, but we have already proved that P of E is always less than or equal to 1, so it is a finite quantity. So I can always take P of E on this side, so P of E complement turns out to be 1 minus P of E. So what we get from result 1 is probability is always between 0 and 1, and probability of E complement would be same as 1 minus probability of E. Okay, so let us prove the next result, which is our result 2. It deals with the monotonicity of probability function. So what it says is that E and F be 2 events such that E is contained in F. So you have situation like this. This is E and this is F. Then it says probability of E is less than or equal to probability of F. So this is called the monotonicity property of probability function. What it says is if you have a smaller set which is E, it will have a smaller probability than probability of F, where F is a bigger set. So the monotonicity of probability function means the smaller set gets the smaller probability and larger set gets the larger probability. Not only that, if E is contained in F, then probability of F minus E is same as probability of F minus probability of E. So this is again very useful result, a simple result but very useful result, which I will be using very frequently in this course. So the idea is very simple. E is contained in F, F minus E is this portion. So this is F minus E. Now if I see F is related with F minus E is, I can write down my F as E union, this is E, and I take its union with F minus E. If I do that, I get whole of F. Now one advantage of doing that is E and F minus E are disjoint. So you can see this is E, this is F minus E, they are disjoint. So probability of F is same as probability of E union F minus E, but E and F minus E are disjoint. So this probability is same as sum of the individual probabilities, which is by axiom 2. But we also know that probability is always non-negative, so probability of F minus E is always greater than or equal to 0. So this probability sum will be greater than or equal to probability of E. So what you get is probability of F is greater than or equal to probability of E, which was the monotonicity property. That means smaller set gets the smaller probability. Now, if I see this thing over here, if I take P of E over here, then probability of F minus E becomes probability of F minus probability of E. But I can always take P of E over here because P of E is a finite quantity. And you know that if you are a finite quantity, then law of cancellation holds, which is equivalent to saying that you can take the expression on one side of equality to the other side. So if I see this gives me probability of F minus E is same as probability of F minus probability of E. So that proves this result. So that was result 2. Now let's look at the next result, which is result 3. What it says is if E1 and E2 are two events, then probability of E1 union E2 is same as probability of E1 plus probability of E2 minus probability of E1 intersection E2. Now note that this property doesn't look very surprising. Why? Because probability is a measure. So if you have to look at what is the measure of E1 union E2, measure of E1 union E2 would be same as measure of E1, measure of E2, but then what is happening is the measure of E1 intersection E2, which is common to both, I have added in both. So that has been added twice. So I have to subtract it once. So that is how you get minus P of E1 intersection E2. So again I use those axioms. So I have to somehow write down E1 union E2 as sum of disjoint events. That is not difficult. Again I can write the Venn diagram. So this is E1, this is E2. Now E1 union E2 is this whole region, and that I write down as whole of E1 and E2 minus E1. These two are disjoint. So P of E1 union E2 becomes P of E1 union E2 minus E1, but since they are disjoint, probability of this union would be sum of the individual probabilities. So I have got P of E1 union E2 as P of E1 plus P of E2 minus E1. Now I try to see what is P of E2 minus E1. Now if we try to look at E2 minus E1, so let us see, this is E1, this is E2. So E2 minus E1 is basically this portion. Now note that this portion can always be written as, if I remove from E2 the common portion E1 intersection E2, which is this portion. So E2 minus E1 can always be written as E2 minus E1 intersection E2. But this portion E1 intersection E2 is contained in E2. So probability of E2 minus E1 would be same as probability of E2 minus E1 intersection E2, but this quantity is contained in this. So by a last result, this probability would be same as P of E2 minus P of E1 intersection E2. So that is using the last result, which says that E is contained in F would imply that probability of F minus E is same as probability of F minus probability of E. And that is what was happening over here. Probability of E2 minus E1 is same as this, but this quantity is contained in this. So probability of this, which is same as probability of this, so probability of this would be same as probability of E2 minus probability of E1 intersection E2. Now if I put this over here, I get P of E1 union E2 as P of E1, and this quantity then becomes P of E2 minus P of E1 intersection E2. Sorry, this would be E1 intersection E2. So you get P of E1 union E2 as same as P of E1 plus P of E2 minus P of E1 intersection E2. So that is what this result says. Now let's look at some generalization of this result. This result for union of two events. Now suppose you are having union of n events. So what it says is for events E1, E2, En, where n is greater than or equal to 2, let us define P1n as sum of probabilities of all events taken one at a time. So here I am taking events one at a time. So P of 1n is P of E1 plus P of E2 plus P of En. P2n is sum of probabilities of joint occurrence of two events. So P of Ei, Ej. So that means I take two events, any two events, I look at the probability of their joint occurrence, which is E1 intersection, Ei intersection Ej, I sum over it. Now note that here I have made sure that indices are I less than j. This is to make sure that P of E1 intersection E2 comes only once. If this condition I less than j was not there, then P of E1 intersection E2 would also come, and P of E2 intersection E1 would also come. So just to avoid that kind of a situation, I have made a condition on the subscript here that I should be less than j. Now in general, PRN is probability of joint occurrence of R events taken at a time. So P of EI1, EI2, EIR. So I look at joint occurrence of all R occurrences taken together. Now certainly this will have sum of how many elements? I have to choose R out of n. So this will be a sum of n choose R elements. And similarly P and n, probability of joint occurrence of all n taken together. So that means P of E1 intersection E2 intersection En. So under these notations, probability of union I is equal to 1 to n EI is same as P1n minus P2n plus P3n plus minus 1 to power n minus 1 Pnn. So there are alternate signs, negative and positive. We start with probability of sum of probabilities of events taken one at a time minus sum of probabilities of events taken two at a time, then alternate sign plus sum of probabilities of events taken three at a time, then plus minus 1 to power n minus 1. Note that with 2 negative sign is coming, with 3 plus sign is coming. So with n the sign would be minus 1 to power n minus 1, and Pnn, which is probability of joint occurrence of all events taken together. Now this result can be proved using mathematical induction. We have already seen that P of E1 union E2 is same as P of E1 plus P of E2 minus P of E1 intersection E2. This we have already seen. What is P of E1 E2? Only two events are there, E1 and E2. So this is sum of probabilities of events taken one at a time. What is E1 intersection E2? Probability of both the events taken together. So we have already proved this result for n is equal to 2. So what I'll do is I'll use the mathematical induction to prove this result. So as I said, the result is 2 for n is equal to 2, which is basically the result 3. Now assume the given result holds for any collection of m events. Then I'll prove that result also holds for any collection of m plus 1 events. So I consider m plus 1 events E1, E2, Em plus 1. I consider their union. I write down this as union of two events. One event is union I is equal to 1 to m EI, and the second is Em plus 1. So union of two events. Now I apply the result for two events which we have already proved. So this is same as probability of the first event plus probability of the second event minus probability of intersection of the first event and the second event, which is this. I try to simplify this union. This is probability union I is equal to 1 to m EI plus probability of Em plus 1. Now this union, this intersection can be distributed along with each of the EIs. So this is same as union I is equal to 1 to m EI intersection Em plus 1. So this is from the basic set theory that your intersection gets distributed over unions. Now advantage of doing this is that now if you look at the probabilities, I am only talking about probabilities of union of m events only. Here also I have m events, here also I have m events, and I have already assumed that the result holds for any collection of m events. So this is same as P1m minus P2m plus P3m plus minus 1 to power r minus 1 PRm plus minus 1 to power m minus 1 PMM. This is this part, because we have assumed that result holds for m events. Then P of Em plus 1 is anyway there. Now I apply this result for m events over here also. So minus remains outside. Then union of m events would be T1m. I'm using the different notation now, T1m, because the events involved are different. T1m minus T2m plus T3m plus minus 1 to power r minus 2 Tr minus 1m minus 1 to power m minus 1 Tm. The reason for taking here minus r minus 2 would be clear, because what I am going to do is I'll combine P1m with Pm plus 1, P2m with P1m, P3m with T2m. So I'll combine minus 1 to power r minus 1 Prm with minus 1 to power r minus 2 Tr minus 1m. So that is the reason for writing down Here not r minus 1, r minus 2. So of course these PRMs we know, these are among these events E1, E2, EM, I take r at a time. So EI1, EI2, EIR and those subscripts. What happens in TRM? I still take r events at a time, but now my events are EI intersection EM plus 1. So I is varying, M plus 1 is fixed. So this is summation over I1 less than I2 less than IR between 1 to M, because this is union for M events. Then intersection of R events, so these are intersection of, let us say one of them, EI1 intersection EM plus 1, this is common to all of them, EM plus 1. Intersection EI2 intersection EM plus 1, intersection EIR intersection EM plus 1. So since this EM plus 1 is common and you are talking about only intersection, you can as well consider EM plus 1 only once. So this is same as summation 1 less than or equal to I1 less than I2 less than IR less than or equal to M, probability of EI1, EI2, EIR and EM plus 1. So this is what you got. So now let us look at what happens to P1M plus P of EM plus 1. So this was P of E1 plus P of E2 plus P of EM plus P of EM plus 1. So this becomes P1M plus 1. So that means you have M plus 1 events E1, E2, EM and you are taking sum of probabilities of taking one at a time. So this is what P1M plus 1 becomes. Now let me slightly go back to the last slide. If you look at P2M, what is happening in P2M? I am considering joint occurrence of 2 among E1, E2, EM. What is happening in T1M? I am considering one of the E1, E2, EM and the second one is EM plus 1. That is what is happening in T1M. T1M means one of them is among, because I1, I2, IR is between 1 to M, so one of them is among E1, E2, EM and the second one is EM plus 1. So this is also joint occurrence of 2. P2M is also joint occurrence of 2. When I am taking 2 among E1, E2, EM, which was the part of P2M, so they are taken care of. Then there is a possibility that one of them is among E1, E2, EM and the second one is EM plus 1. That is taken care by T1M. So this gives me P2M plus 1 altogether. So that means when you are considering the sum of probabilities of any two events among A1, A2, AM plus 1 taken 2 at a time. Similarly, when I am talking about PRM plus TRM minus 1M, what is a PRM? In PRM I take joint occurrence of R of E1, E2, EM. So joint occurrence of R events among E1, E2, EM. What I do in TR minus 1M, I look at joint occurrence of R minus 1 among E1, E2, EM and the next one is EM plus 1. So when I combine the two, this gives me expression for joint occurrence of any two of P1, P2, PM. So that is why you get PRM plus 1. Sorry, not joint occurrence of 2. When I talk about PRM, I am talking about joint occurrence of any R of the events among E1, E2, EM. When I am looking at TR minus 1M, I am talking about joint occurrence of any R minus 1 events among E1, E2, EM and one of them is EM plus 1. So when I combine the two, I get the joint occurrence of E1, E2, EM and EM plus 1 when R are taken at a time. Now let us look at TMM. What was TMM? Let us go back to the slide. TMM was when all of them are taken together and EM plus 1 is there. So that means M of E1, E2, EM and EM plus 1. So that is a probability that all of them have been taken together. So this is what PM plus 1, PM plus 1. So if you combine all this, you get the desired result. So notations are a little bit involved, but the expression is simple. You first look at sum of all probabilities taken one at a time, then consider alternate sign minus sum of probabilities of all events taken 2 at a time, alternate sign sum of probabilities of all events taken 3 at a time, plus minus 1 to M plus 1, sum of all events taken together. So this is what the result is for M plus 1. So for example, if you have to write down this event for 3, what would be the case for 3? So if I have to write down probability of E1, union E2, union E3, this would be same as all taken one at a time. So P of E1 plus P of E2 minus plus P of E3. Now with alternate sign, all taken two at a time. So 3 choose 2. So those will be 3 elements, E1 intersection E2 minus E1 intersection E3 minus E2 intersection E3. Then there is alternate sign plus all taken together, all 3 taken together. So that is P of E1 intersection E2 intersection E3. So simple result, but very useful result. Now note that probability union I is equal to 1 to m ei plus 1 is the probability that at least one of the ei occurs. That is what this probability gives you. So if you have to find in some situation that what is the probability that at least one of the given events would occur, just find the probability of union and you can use this inclusion exclusion principle. Why it is called an inclusion exclusion principle? Because to begin with you added all the probabilities, then you realize that they were common elements, they have been subtracted twice or more than twice, you look at minus and keep on doing it.